In previous video lecture, we studied about natural sampling, where xt is multiplied with rectangular pulses, which has a time period of sampling time period of Ts and width T1, and we got this type of sampled signal. In frequency domain, xt has frequency transform, this is xf, and for rectangular pulses we got this type of frequency transform, which depends upon the strength of these impulses depends upon ak, where ak is written with this formula sin omega T1 by 2 divided by k pi. And in the previous video lecture we also saw that in case of impulse train, if impulse train was there, the strength of impulses are same, but in case of rectangular pulses the strength of impulse train varies, and even it may be 0 at some points, where k equal to integral multiple of Ts by T1. If we use this formula, k omega s T1 by 2, if this angle is integral multiple of n pi, then if k is equal to 2 n pi divided by omega s t, and using 2 pi equal to omega s T1 and using 2 pi equal to omega s into Ts, if we use k equal to omega s Ts divided by omega s T1 into 2 pi is written as omega s t into n. So, we will get, if k is equal to n Ts by T1, we will get ak equal to 0. So, corresponding to that those value of k in the frequency transform of rectangular pulses, we will get 0 strength of impulse. Okay. So, this way we got frequency transform of rectangular pulses. Now, for obtaining frequency transform of sample signal, we will have to take convolution of xf and sf. So, if we will take convolution of this signal with this is impulse at 0, we will get same type of signal, and this height, the strength of xf, this will be modified with the factor that is equal to the strength of this impulse. This is not necessarily 1, this will depend upon a naught, and a naught is average value of this signal. In the Fourier series expansion, a naught always represents average value of a signal. So, average value of this signal is T1 by Ts. So, here a naught equal to T1 by Ts. So, the height of xf will be modified with the factor of T1 by Ts, and at this point ak is 0. So, we will get, if we will take convolution of this point and this signal, we will get 0 signal. So, this type of frequency transform of sample signal we will get. Now, if we want to extract the original signal, we can use a filter here. If we set cutoff frequency of filter like this, we will get back the original signal. So, this way sampling can be done here. Next, we are going to study flat top sampling, but before studying this, we will solve a question which came in GATE, and which was based on natural sampling. This was asked in GATE 2003, and this was of 2 marks. So, I am reading the question. Let xt equal to, xt is given, xt equal to 2 cos 800 pi t plus cos 1400 pi t. This is xt. Xt is sampled with the rectangular pulse train shown in figure. Rectangular pulse is given in the figure. This is pt, rectangular pulse. I have denoted it by st, and this is minus t naught by 6, t naught by 6, and this is T naught. The rectangular pulse is periodic, its time period is T naught, and the pulse width is T naught by 3. So, the pulse width is 1/3 of its time period, that is T 1 is equal to T naught by 3. This is 1/3 of the time period. Now, the only spectral components in kilohertz present in the sampled signal in the frequency range of 2.5 kilohertz to 3.5 kilohertz. The frequency range is given between 2.5 kilohertz to 3.5 kilohertz, and we need to find that in the sampled signal which frequency component is present between this range. So, we have given 2.5 kilohertz to 3.5 kilohertz. So, if we make AK for this PT, we will write AK equal to sin k omega s T 1 by 2, where T 1 is the pulse width. In our derivation we use like this, minus T 1 by 2, and this was plus T 1 by 2, and then we got this formula. So, at the place of T 1 by 2 we have T naught by 6. So, we will use T 1 equal to T naught by 3. If T 1 by 2 equal to T naught by 6, T 1 will be T naught by 3. So, we will use T 1 equal to T naught by 3 divided by, this is k pi. So, A 0 will be, we will have non-zero value of A 0. If we use k equal to 0, we will have some value. A 0 is equal to, this is average value. So, this will be k omega s T 1 by 2 divided by, at the place of k we will use 0. So, if theta is 0, sin theta equal to theta, if this tends to 0, we will use sin theta equal to theta, k omega s T 1 by 2 divided by k pi, k tends to 0. So, this we can write this, is omega s T 1 by 2 pi omega s T 1 divided by, at the place of 2 pi we can write omega s T s. So, this is T 1 by T s, and T 1 by T s is equal to, T 1 is T naught by 3, T s equal to T naught. So, we will get 1 by 3. So, we will get at 0 frequency, we will get impulse with a strength 1 by 3. Similarly, A1, for A1 the envelope is like this. This is the envelope for AK. Similarly, we will get some non-zero value of A1, some non-zero value of A2, but here A3 will be 0. This is A0, this is A1, this is A2, and A3 will be 0. So, here we will get no impulse. Now, this is Fs, this is 2 Fs, this is 3 Fs, and sampling frequency is, and T naught is given as 10 to power minus 3 second. So, frequency is 1 kilohertz. So, at 1 kilohertz we have impulse, at 2 kilohertz we have impulse, at 3 kilohertz we have no impulse. Similarly, the mirror image will be in the left half. So, and we have xt, in xt we have two sinusoidal signal. One has two type of sinusoidal signal, one has frequency. If you divide it by 2 pi, we will get 400 frequency, 400 hertz frequency, that is 0.4 kilohertz, and here we will get 0.7 kilohertz. So, if 0.4 kilohertz and 0.7 kilohertz signals are present in xt. If we make xf, we will get an impulse at 0.4 kilohertz and at mirror image at minus 0.4 kilohertz, then again at 0.7 kilohertz, this is 0.7 kilohertz, and mirror image at minus 0.7 kilohertz. Okay. If we will take convolution of xf with this signal, we will get same signal. We will get, if we take convolution with impulse at 0, we will get minus 0.4 minus 0.7 kilohertz component, 0.4 kilohertz and 0.7 kilohertz. So, none of the component lie in this range. Okay. So, when we will take convolution of this signal with 1 kilohertz impulse, we will get 1.4, 1.7, then convolution of 1 with minus 0.4, then we will get 0.6 k, and convolution of 1 with minus 0.7 k, we will get 0.3 k. So, these frequency component also do not lie in our range. Next, take convolution of this signal with 2 kilohertz. So, this will be 2 minus 0.7, 2 minus 0.4, 2 plus 0.4 and 2 plus 0.7. We will get 1.3, this is 1.6, this is 2.4 and this is 2.7 kilohertz. So, 2.7 lies in our range. So, we will write here, we will note it separately, 2.7 kilohertz. Then next we take with A3, but there is no impulse at this position. So, we will take with A4. A4, if we calculate A4, we will get negative sign here, but in frequency transform or when we do sampling, only the magnitude of xf is important. So, whenever we will get negative impulse or negative value, we can take a mirror image of this about x axis. We can take modulus of this, and A4 we will certainly get if you calculate from this formula. If you calculate from this formula, we will at A3 we will get no impulse, again at A6 we will get no impulse, again at A9 we will get no impulse, but at A4 certainly there will be an impulse. So, does not matter what is the height, we will have to take convolution. So, at 4 kilohertz, if we take convolution, we will get 4 minus 0.7, 4 minus 0.4, 4 plus 0.4, 4 plus 0.7. This is 3.3 kilohertz, this is 3.6 kilohertz, 4.4 and 4.7. Out of these values, 3.3 kilohertz lies in this range. So, we will note it down separately. Now, if we will take convolution with 5 kilohertz, the minimum value we will get is 5 minus 0.7, that is 4.3, and that does not lie in this range. So, the only two values 2.7 kilohertz and 3.3 kilohertz, these two components lies in this range. So, this will be answer. What can be mistake here if we do not calculate it properly, like in impulse train. In impulse train, we always have impulse of same strength even at k equal to 3. So, if we do not take care here, we will use an impulse here, and we will get, and if we take convolution of this signal, this is at 3 kilohertz with xf, we will get 3 minus 0.7, 3 minus 0.4, 3 plus 0.4, 3 plus 0.7. This is 2.3, this is not in range, this is 2.6, this is in range, this is 3.4, this is in range, and this is 3.7, this is not in range. These two values also come in the range, 2.7, 3.3, 2.6 and 3.4, and all 4 values, these 4 values are also given in one of the options. So, this can be mistaken here. So, we will have to carefully take in the case of rectangular pulse which component is 0. In natural sampling, we multiplied x t with a rectangular pulse and which is height 1, and we got, if we multiply these two signals, it has height 1. So, if we multiply this signal with height 1, there will be no change. So, we will get this type of signal here. This signal has varying height, but in flat top sampling we want to get a constant height, that is a flat height, this type of signal. So, first I am writing down, I am not writing the impulse train or signal with which this x t has to be multiplied. I am first writing down the sampled signal. In this case, in flat top sampling, we want to get a signal which has constant height. Suppose we start from here, we start from 0. So, and this is sampling interval. So, we will start with this height and we want this height to be constant. Now, then at next sample the height is different and this is the difference in height. So, this height and this value will be held constant till the next sample occurs. This is 2 Ts. So, at this point we will get this type of height. Next, height is again increased with this much difference. We want to get this type of signal. This is flat top sampling. I am first making circuit, how in the circuit diagram or practically how this signal can be obtained from this. This is suppose input voltage and we have to get this type of signal. So, I am first drawing the circuit and then we will try to obtain how to get this signal mathematically from x t. So, first I am writing making the circuit. We will take a negative feedback amplifier or negative feedback, this is called buffer circuit, and suppose this is input voltage. Here we will have a switch, a MOSFET. This is controlling signal. Again a voltage buffer. So, this circuit is called sample and hold circuit, ECE circuit, and I have drawn the simplest sample and hold circuit just to explain the concept. Suppose this is this input, this is analog input, and at capacitor we want to get this type of flat top signal. So, in this circuit analog input is applied here, and using the circuit it is we get this type of output signal. This is also an analog signal. Now, this analog signal is fed to analog to digital converter. So, this way we take an analog signal, we sample it using this circuit, we get flat top signal, and then signal is sent to analog to digital converter, and this way then signal is digitalized and then further processed for communication. Now, this is a negative feedback circuit. So, potential of this point and this point will always be same. So, suppose this is input voltage, here we will get input voltage, and this switch is, I am drawing like this type of switch, this is open and close at high frequency. So, whenever this switch is closed or whenever signal is applied here, it starts conducting and V input comes here. So, capacitor is charged with input voltage. Now, when the switch is closed, when the switch is closed, the current can flow through here, through this path. So, the capacitor voltage, as soon as the switch is closed, capacitor voltage will become input voltage. But when the switch is opened, I am opening it here, there is no path for capacitor to be discharged, because ideally, if we talk about ideally no current can flow in the amplifier in this buffer. So, there is no path for capacitor to be discharged. So, whenever this switch is opened, capacitor can hold its voltage, its output. And again, the potential of this point and this point is same. So, if it is at Vc, this point will also be at Vc, and we will get output voltage Vc as constant whenever this switch is opened. Suppose this is instant t1, and before t1 it has some value v1 or v0, and after t1 the value is v0. So, before t1 the voltage of capacitor would be v0, and at instant t1 the switch is closed. Now, if the switch is closed, current will flow from here, and the voltage of capacitor will, ideally the voltage of capacitor will be instantly v1. Now, after the close, when the switch will open, the capacitor will hold its voltage v1. So, we will get constant voltage up to v1. Ideally, whenever the switch is closed, at the same instant capacitor voltage must be equal to this voltage, but due to resistance of switches, the switch has some non-zero resistance, the capacitor voltage is not able to change instantaneously. So, I am drawing it again, I am zooming this part. Suppose this is V0 and this is V1 and this is instant T1, and before T1 the capacitor voltage was V0. Now, suppose at T1 the switch is closed. Now, suppose the switch has some resistance R. So, now capacitor voltage will try to change from V0 to V1, but because it has some resistance R, it will have some time constant, and capacitor voltage will now grow like this. It will make a first order RC circuit. At high frequency, even a conductor has, at high frequency, even a conductor offers some inductance, or even a conductor has very small value of inductance. If and the reactance offered by this inductance is omega L. If frequency is low for a conductor which is not a coil, inductance is very less. So, at low frequency it will offer negligible reactance, but at high frequency even a conductor may offer some reactance. So, actually the voltage across the capacitor voltage does not take this form, it takes a second order form which changes like this. Now, if analog to digital converter, suppose analog to digital converter takes this voltage, and ideally analog to digital converter should take V1 and convert V1 analog voltage to digital output. If analog to digital converter takes this value, and suppose this error is more than the resolution of analog to digital converter. So, corresponding to V1, analog to digital converter has 1000 output. If the input voltage, or if the difference between these two voltage is more than the resolution of analog to digital converter, its voltage will, its output will be changed. So, we will get error. So, the variation in the capacitor voltage must be less than the resolution of analog to digital converter. So, suppose this is the boundary for resolution of analog to digital converter. So, at this point it will give error, but this variation is within the resolution of analog to A to D converter. So, this value can be taken, even this value can be taken. So, before giving this signal to analog to digital converter, we will have to wait for this time. This makes a second order variation. Suppose this is input voltage, here resistance, so we will get R, L and C. So, the output across capacitor will make this kind of waveform. So, we will have to wait for this time, and this time is called acquisition time. This time is called acquisition time, and after acquisition time only the voltage can be given to analog to digital converter. This is T, suppose this is T acquisition time. So, we cannot open the switch at this point. The switch will be opened after the voltage across capacitor becomes in this range. Now, suppose at this point, but at this point switch is opened. So, now this is opened. Now, ideally the voltage across capacitor must be constant, but if we talk about non-ideality, even this buffer, ideally there should be no current in the differential amplifier, but if we talk about non-ideality, there will be some constant current in the amplifier. So, suppose this current is IC, then after this point this is positive. So, the current will have some path, IC will be flows like this, then the voltage of capacitor will decrease, and if current through a capacitor is constant, the rate of change of voltage dVc by dt is equal to C by C. Now, if current is constant, this whole quantity will be constant. So, delta Vc can be written as I by C, IC capacitor current divided by C into time. So, but this current is very small. So, when the switch is opened, capacitor voltage will not be constant, it will decay through constant rate. So, this will be the actual voltage across capacitor. We want constant voltage, but we will have this kind of voltage. So, this rate is the rate at which capacitor voltage decreases. This is called droop rate. Now, again the total drop in capacitor voltage, this drop should not be more than the resolution of analog converter, because if the change in voltage across capacitor is more than the resolution of analog to digital converter, then at this point analog to digital converter will give some output, but at this point the digital A to D converter will change its digital output. So, this must be less than the resolution of A to D converter. Now, if you want to reduce the variation in capacitor voltage, the value of capacitor should be high, but if the value of capacitor is high, the change in capacitor voltage from V1 to V2 will be slow. So, there is a trade off in the value of capacitor. So, if the capacitor is increased, if capacitance is increased, droop rate will decrease and acquisition time will increase. If we analyze it taking as first order circuit, the time constant of first order circuit is RC, and if capacitance is increased, the time constant will increase, and if time constant is high, we will say that the transient is slow, the change in capacitor voltage is slow. So, by increasing C, acquisition time will increase. So, this is how we get flat top signal using sample and hold circuit. Now, for analyzing the frequency component in sampled signal, we will have to take Fourier transform of or frequency transform of sampled signal. Suppose xt has frequency transform as we have taken before. This is xf. The frequency transform of xf is known or xt is known. We have sampled signal. Now, we have to analyze frequency transform of xt. We have studied that how this signal can be obtained practically, but for studying frequency transform of xst, we need to know mathematically from xt to xst can be obtained. If we multiply this signal with ideal impulse, if this signal is multiplied with impulses with sampling interval Ts, this is Ts, this is 2 Ts, we will get impulses as we got in ideal sampling of varying strength. These are impulse with varying strength, and the strength of impulse depend upon, suppose here we have x0. So, the strength of this impulse will be x0 at this point. Suppose this is Ts, we will have a strength of this impulse will be x Ts, but what we need? We do not need this signal, we have to do flat top sampling. So, from this signal we have to get this type of signal. So, we will again have to do something here. This signal has a strength x0 and we want x0 constant value. So, if we take convolution of this signal, this modified impulse train with this signal, this we will name it as, this signal is x, or this signal is ut minus ut minus ts. If we take convolution of this signal with impulse x0, we will get x0. Now, if we take convolution of this signal with this impulse, this has a strength of xts. The value of this signal, the height of this signal will be multiplied at this position. The height of this is height 1. If we take convolution of this signal, the total height will be, the equivalent height will be 1 into x0. So, we will obtain here as x0. At this point, if we take convolution of this signal with impulse at xts, we will get height as xts. So, in flat top sampling, we have to take convolution of modified impulse train, that is obtained by multiplying xt with impulse train. We have to take convolution of modified impulse train with this signal. This is also called this is HT for zero order whole circuit. So, we have xst, we can write xst as xt multiplied by xt into multiplied by ideal impulse train and then we took convolution with ut minus ts. So, in frequency transform, we will take convolution of these two signals. So, if we take, or we want to take we will first, for obtaining frequency transform of this signal, we will first obtain frequency transform of this signal, then frequency transform of this signal, and we will, since here convolution, here convolution sign is there. So, in frequency transform, the two frequency transforms will be multiplied. Now, we know that the frequency transform of this signal is, suppose xt has this type of frequency transform. If we multiply xt with impulse train, we will get Fourier transform like this. We will get this type of Fourier transform. Now, we have frequency transform of this signal as here. Now, we have to multiply this Fourier transform with the Fourier transform of ut minus ts. This is so. Now, we have to obtain Fourier transform of this signal. Earlier, we had obtained that, suppose this is 0, this is Ts. In the rectangular, in natural sampling, we obtained that if it is minus T1 by 2, this is T1 by 2. Okay. This is not periodic. So, we have to take Fourier transform. We write down formula for Fourier transform as minus infinity to plus infinity f t e to power minus j omega t dt. So, this is 0 to T s, f t is, this height is 1 into e to power minus j omega t dt. This is minus 1 by j omega into, if we put T s, we will get minus j omega T s minus 1, or f omega is equal to 1 by j omega into 1 minus e to power minus j omega T s. This is not omega s, this is variable omega, which I have written here. But in frequency transform, we have to take convolution here. We want to get the Fourier transform of flat top signal. So, only magnitude is important. So, we need to take magnitude of this signal. Now, for taking magnitude of this signal, whenever you get here it is 1 and some power of, some complex power of, or this is some complex function. So, you always do this type of calculation. You take e to power something common, such that if here e to power minus j theta, you have to obtain e to power plus j theta here. So, I am taking common e to power minus j omega T s by 2. So, at the place of 1, we will get e to power j omega T s by 2 minus, here we will get e to power minus j omega T s by 2. So, we will get f omega equal to 1 by j omega e to power minus j omega T s by 2 into e to power j theta minus e to power minus j theta equal to 2j sin theta, 2j sin omega T s by 2. J and j is cancelled. This is theta. And if you want to take magnitude of f omega, magnitude of this quantity is always 1. So, we will get 2 sin omega T s by 2 divided by omega. The another method for obtaining Fourier transform, I am doing it by another method, and we will verify this result. Instead of taking this signal, I am first finding Fourier transform of, suppose this is f t, and instead of taking from 0 to T s, I am taking minus T s by 2 to plus T s by 2. So, for f omega, we will write the formula x t into e to power minus j omega t dt integration from minus infinity to plus infinity. This is only in the range minus Ts by 2 to plus Ts by 2, minus Ts by 2 to plus Ts by 2, xt is equal to 1 e to power minus j omega t dt. So, if you integrate it, you will get 1 by minus 1 by j omega e to power minus j omega Ts by 2 minus e to power j omega Ts by 2. If you solve it, you will get 2 sine omega Ts by 2 divided by omega f omega. Now, we have obtained Fourier transform of this signal, but we have to take Fourier transform of 0 to Ts. Now, if we shift, suppose this is f t, we will write f t has a Fourier transform of 2 sine omega Ts by 2 by omega. Now, we have to shift this signal by Ts by 2. So, if this is f t, this signal can be written as f t minus Ts by 2. Now, if we have Fourier transform of f t as f omega, f t minus t naught has Fourier transform of f omega multiplied by e to power minus j omega t naught. So, f t minus Ts by 2 will have Fourier transform, f t minus Ts by 2 will have Fourier transform 2 sine omega Ts by 2 divided by omega into e to power minus j omega Ts by 2. Now, this is the signal, this is this signal for which we want to take Fourier transform. Now, if we take modulus of this signal has e to power minus, the modulus of e to power minus j omega Ts by 2 is 1 over. This has only phase contribution, though no magnitude contribution. So, if we will take magnitude, we will again get 2 sine omega Ts by 2 divided by omega. The shifting in time domain only contributes phase shift in frequency domain. So, there will be no magnitude, does not matter how much you are shifting it left or right, there will be no change in the magnitude of Fourier transform of this signal. So, this signal has Fourier transform as 2 omega Ts by 2 divided by omega. If you plot graph for this, we will get, suppose this is x omega, this is frequency transform of the modified impulse train, and which is modified by xt. So, the Fourier transform will be the Fourier transform of ideally sampled signal. Now, we have to multiply the Fourier transform of this signal with this one. If we plot, this is again sinc type function. So, at whenever omega equal to 0 or f equal to 0, we will get 0, we will get 0 by 0 form. So, this will be omega Ts by 2 divided by omega, here 2 is there. So, this will be Ts. The height we will get as Ts, and whenever omega Ts by 2 equal to 0, whenever this angle is integral multiple of pi, we will get f omega as 0, or whenever omega is equal to 2 n pi divided by Ts, or whenever f is equal to 2n pi by Ts into 2 pi, we will get f omega 0. So, whenever f equal to n by Ts, where n is an integer, so whenever frequency is integral multiple of sampling frequency, we will get f omega as 0. And this is sampling frequency. We have already done these things in the first lecture of sampling theorem. So, I am not going to explain how Fs came here. Those who do not understand, you first need to watch the first lecture of sampling theorem, then there was second lecture, and this is the third lecture for sampling theorem. So, we will get, if you plot it f omega, we will get this type of signal. Now, since convolution sign is there, if you want to take frequency transform of this signal, we will have to multiply these two signals. Now, this height is Ts. Suppose if we multiply at this point, we will get, suppose this height was constant at 1, then we would get the same signal what is here, but as you increase the frequency, the gain is decreasing here. So, at this point, if the constant gain was here, we would get the same signal. So, first I am drawing with a dotted line for constant gain, but gain is not 1, even if it is not 1, we will get 0 value at this point only. We will get 0 at this point, and same point at omega equal to 0, but from here to here the value will be decreasing. So, we will get like this type of graph. The gain is decreasing as the frequency is increased. So, in flat top sampling, due to this part or due to frequency transform of this part, the high frequency component of this signal has less gain, or we can say that the high frequency component of original signal is attenuated. Now, for obtaining the original signal, if you take filter, you cannot get original signal, because at high frequency it has lesser gain. So, now if the pulse width is increased here, suppose this pulse width is increased, if this pulse width is increased, this is Ts. If we increase Ts, what will be change on this frequency transform? This is 2 sin omega Ts by 2 divided by omega. If Ts is high, consider this node, the first 0 will occur when this angle is pi, when omega Ts by 2 equal to pi, or when omega is equal to 2 pi by Ts, or when frequency is equal to 1 by Ts. Now, if Ts is increased, or the pulse width of the signal is increased, at lesser value of frequency, this will have 0 component, or we can say that this signal will, this graph will decrease rapidly. Suppose now f will decrease, now this will be 0 earlier than this point. So, we will get this kind of graph. So, for this, in this case, for high frequency attenuation is even higher. So, we will get this type of signal. So, if pulse width is increased, we will have more attenuation for high frequency component. So, for minimizing the error for minimizing the distortion, the pulse width of this signal should be as low as possible. This is also called zero order hold, and the equation of zero order hold is, this is Ht for zero order hold, Ht equal to ut minus Ts so this will be 1 by s. If you take Hs for zero order hold, this will be 1 by s minus e to power minus Ts by s, 1 minus e to power minus Ts by s. This was asked many times in GATE. So, this was all about flat top sampling. Before finishing sampling theorem, I would like to analyze minimum sampling frequency for DSP-SC. DSP-SC is for double sideband suppressed carrier. When we will study analog communication, we will study about DSP-SC, but I assume that you know a little bit about it. In DSP-SC, there is a baseband signal MT, and suppose MT has this type of frequency transform MF. This is multiplied with, or the modulation of a high frequency carrier, the amplitude modulation of high frequency carrier is done by signal MT. So, we get DSP-SC. Formula for DSP-SC is MT cos omega ct. I am not going much detail into the analog communication. I just want to make the Fourier transform of MT cos omega ct, where the frequency of carrier signal is much higher than the frequency of the baseband signal, the MT. So, suppose this is the bandwidth for MT, this is the highest frequency content of MT, suppose this is Fm. If this is in kilohertz, normally the Fc, the carrier frequency, is in megahertz. So, if we want to calculate, so if this is Fm and we want to find out the Fourier transform, these two are multiplication. So, if we want to find out Fourier transform of this signal, we will have to take Fourier convolution of Fourier transform of MT and Fourier transform of omega ct. The Fourier transform of omega ct is Fc is much higher than Fm. So, I am showing it this much length, and Fc is here, and similarly the negative component minus Fc. If we take convolution of these two signals, we will get, if we take convolution of this MF with this much, this signal will be shifted by Fc. So, we will get this point will be Fc plus Fm, and this is Fc minus Fm. Similarly, this point is minus Fc minus Fm, this point is minus Fc plus Fm. Now, once analog the DSP-SC is obtained, or the amplitude modulation is done, this is also an analog signal. Now, this has to be, this is digitalized for transmission. For digitalizing this, we need to take sampling of this signal. We need to take sample of this signal, or we need to do sampling. So, we need the question is, what should be the sampling frequency for this signal? In this signal, the highest frequency content is Fc plus Fm. So, do we need, if we go to, if we write down formula for sampling theorem for a low pass signal or a bass band signal, the sampling frequency must be greater than 2 times of maximum frequency content of baseband signal. So, if we apply this formula, do we need a sampling frequency that must be greater than, do we need this sampling frequency, or it is something else? Those who have studied it, you must be knowing that for digitalizing this signal, the sampling frequency must be greater than 2 into bandwidth of this signal. The bandwidth of this signal is much less than Fc plus Fm. Suppose this is 1 kilohertz. So, the bandwidth will be, this width is 2 kilohertz, and the carrier frequency is 1 megahertz. So, the maximum frequency content will be 1 megahertz means 1000 kilohertz, and this length is 2 kilohertz. So, this will be 1002 kilohertz. So, if we use this formula, we will have to take sampling frequency that is equal to 2004 kilohertz or 2.004 megahertz. This should be sampling frequency, but we know that the sampling frequency must be greater than 2 into bandwidth of this signal. The bandwidth of this signal is 4 kilohertz. So, in actual we need a sampling frequency that is greater than 2 into bandwidth is 4 kilohertz. So, we need a sampling frequency of 8 kilohertz. So, in this case we do not need, we do not have to apply this formula. We have to apply formula for band pass signal. This is a band pass signal. It has a very lesser band, and that is not nearer to origin. That is far away from origin. So, we will use another formula. I have just wrote that formula. I have not derived it. The derivation is difficult, and we do not need that derivation for get. The formula is formula for sampling frequency of a band pass signal is 2 Fc plus Fm divided by k plus 1. Fs must be greater than this and must be less than 2 Fc minus Fm divided by k, where k is an, we studied this formula in the second lecture of sampling theorem, and we also did a numerical based on this formula. And using this formula, I am going to prove that for sampling a DSBSC which has a bandwidth of b, we need a minimum sampling frequency of 2b. Okay. So, in this formula, k is an integer, and Fc is, if this is the signal of which we want to take sampling, we want to do sampling. So, Fc is the centered frequency of this signal. So, in this case, in DSBSC, the centered frequency we will get as the carrier frequency. So, this can be also be named as carrier frequency, and this is not Fm, this is B, this is B. So, Fc is the centered frequency or carrier frequency, and this is bandwidth of the signal. So, in this case the bandwidth is, if the bandwidth of baseband signal is 2 kilohertz, the bandwidth of modulated signal will have 4 kilohertz bandwidth. So, k is an integer. So, Fs must be greater than this quantity, and k has to be an integer, but for obtaining minimum value of Fs, we have to maximize k. And how we will maximize k? If this relation holds then this quantity must be less than this quantity. So, we will use this inequality to find out maximum value of k. We will maximize k so that we could get the minimum value of f s. So, first we are using this inequality 2 f c plus b divided by k plus 1 must be less than 2 f c minus b divided by k. Before proceeding further, f c is centered frequency. If you add this length is f c minus f m, or suppose this length is b, instead of f m I am writing it as b. So, this length will be b. So, this length is f c minus b. Again, this length is, here it is f c. So, this will be f c plus b. If you add these two lengths, we will get 2 f c. So, we will say that the carrier frequency is average of the minimum frequency and the maximum frequency. Suppose the minimum frequency, this is f c minus v, this is the lower frequency and this is higher frequency. So, I am going to write in terms of f l and f h. So, 2 f c is, this length is f l and this length is f h. So, if we add f l plus f h, we will get 2 f c. So, f c can be written as f l plus f h, and this is bandwidth. Bandwidth means this is not f, this is not b, this is also not b, this is the bandwidth. So, we will use here f c minus b by 2 and f c plus b by 2. So, in this case also f l plus f h is again 2 f c, and suppose this is b, then b is equal to, b can be written as f h minus f l. So, 2 f c can be written as f h plus f l, and b can be written as f h minus f l divided by k plus 1 must be less than, this is f h plus f l minus f h minus f l divided by k. We want to maximize k. Here f l will be cancelled, here f h will be cancelled. So, 2 f h by k plus 1 must be less than 2 f l by k, or k into f h must be less than k f l plus f l, or k must be less than f l divided by this is k f h, k must be less than f l divided by f h minus f l, and f h minus f l is b. So, we will write it as f l divided by b, where f l is the lowest frequency of the signal. So, k must be less than f l by b. So, the maximum value of k will be, and k is integer. Suppose suppose FL by B is not an integer, you will have to take the greatest integer. Suppose this is 5.3, so you will take the value of k as 5. K has to be an integer. Okay. Now, for obtaining value of Fs, we will use this inequality. So, Fs must be greater than, for proper sampling, Fs must be greater than 2Fc plus B, and 2Fc plus B is also equal to 2Fh. This must be greater than 2Fh divided by k plus 1. So, if we, and k is less than FL by B. So, Fs must be greater than 2Fh divided by FL by B plus 1. Fs must be greater than 2Fh into B divided by FL plus B. Or Fs must be greater than. Now, in the case of TSB-SC, this width is, suppose for in our example, this is this is 2 kilohertz. So, this point will be, this is 1000 hertz, this is 1002 hertz, and this is 1002 kilohertz, and this is 998 kilohertz. So, FL is equal to 998 kilohertz, and B is, this total width is 2 plus 2 4 kilohertz. So, this is much greater than B. So, we can neglect B in front of FL. So, we will write 2 FH divided by FL into B. Fs must be greater than, approximately. Again, FH is 1002 and FL is 198. These two are approximately same. So, this will be cancelled out, and Fs must be greater than 2 into B. The minimum sampling frequency must be greater than 2 times of bandwidth of the signal, not 2 times of maximum frequency content of DSP-SC.